evening to everyone present here. My name is Devanand, and I'm a postgraduate student at the National Institute of Technology, Trichy. I take immense pleasure to share with every one of you a part of my research that I had done under the guidance of Dr. S. Suresh, Associate Professor, Department of Mechanical Engineering, NIT Trichy. The title of this presentation is Computational Modeling of the Heat Transfer During the Pulsed Vacuum Drying of Mamordica Carrantia. So let me start my presentation now. Here, I want to give a brief introduction about the characteristics of Mamordica carrantia, which is a herbaceous vine native to the tropical and subtropical regions like Asia, Africa, and Caribbean. It is rich in vitamins, nutritional values such as vitamins, minerals, and dietary fiber. Vegetables in general are highly perishable owing to its higher moisture content, which leads to enhanced microbial activity causing deterioration. So this reduces the shelf life of this Mamordica carrantia to 4 days when stored under ambient condition, owing to a higher moisture content of about 90%. So the prevention of this wastage and losses incurred due to this moisture content is of a major interest in this research. So how can we improve the shelf life? So drying is one of the most ancient methods of food preservation, as it removes the moisture content, thereby improving the shelf life. The dehydration, it also results in a reduction in the weight of the product, thereby aiding in post-harvest handling and transportation of the product. These are some of the types of drying processes widely used for improving the shelf life of a product. I do not intend to go into details about all of these drying methods, so let me briefly talk about the open air drying process, which is also known as direct solar drying process. It is one of the widely used methods owing to its simplicity. In this method, the drying is performed with the help of the heat harnessed from the sun. It usually requires large areas, open spaces, and often result in long drying times. So one of the major disadvantage of this method is the contamination of the product when you keep it in the atmosphere from the birds and insects. So in order to overcome such difficulties, alternate drying methods have been developed over the years thanks to advancements in science and technology. One such method is vacuum drying, which, as the name suggests, it uses vacuum pressure to vacuum pressure conditions to reduce the drying time. This process is relatively cheaper when done under a huge scale and produces higher quality dried products. As the drying pressure reduces, by the thermodynamic law, the drying temperature also reduces. This enables the drying process to be carried out at a reduced temperature of about 30 to 75 degrees Celsius. Therefore, this method is conducive for drying heat-sensitive fruits and vegetables. Pulsed vacuum drying is a modified form of vacuum drying where the dehydration is achieved by cyclical pressure drops, which maximizes the energy efficiency of the overall process, and it also retains the food quality. This novel process gives an obvious improvement in drying rates in comparison to the continuous vacuum drying process. So this slide shows the objective that we have initially set for this part of the research, that is to perform a transient thermal analysis study using COMSOL and to identify the influence of various system parameters and drying characteristics. Also here you can see the experimental setup that we have fabricated for this research work. So moving on to the next slide, here we can see the operational parameters that we have chosen to control the drying environment. Here I want to explain what a pulsing ratio is. For instance, a pulsing ratio of 15:5 implies that the drying environment is kept in vacuum for 15 minutes, followed by the restoration to atmospheric pressure and maintained again for 5 minutes. Now, let me talk some key points about the computational modeling of this process using COMSOL. Due to time constraints, I do not intend to go on details about the model definitions and such, but here you can see that we have used extremely fine meshing for this computational study. The geometry, it was meshed using an automatic physics controlled mesh. The grid independence test was performed to arrive at an optimal element size, which was set to extremely for all simulated cases. So in this slide and the next slide, you can see the temporal variation of the system parameters. These two slides depicts how the volume fraction changes at set temperature, pressure, and pulsing ratio at 3 different times. In the initial 1 hour of heating, only a small region of the sample near the heating plate will reach 0 moisture content, which is represented by the blue region in liquid volume fraction distribution. A majority of the liquid will remain near the top boundary. As the time progresses, the region without the liquid further shifts up as the sample temperature increases and the more moisture is removed from the system. After almost 8 hours of heating, the liquid volume fraction reduces further to order of 10 to the power of -3 throughout the sample. This shows the temporal variation of temperature at two different drying times. In the initial 1 hour of heating, only a small region of the sample near the heating plate will attain temperature close to 60 degrees Celsius, which is the hot plate temperature. After almost 8 hours of heating, a larger portion of the sample will be in the higher temperature region. As the experiment progresses further, the temperature of the sample approaches the temperature of the wall at the bottom boundary to achieve thermal equilibrium. So this slide shows the evaporation rate at three different drying times. At the initial 1 hour of heating, the water closest to the heating boundary undergoes phase change to vapor. Gradually, all the vapor is removed from the zone and evaporation rate decreases to zero. This evaporation zone then shifts upward as the time increases and more liquid vaporizes in the bottom layers. The shift in the evaporation zone continues till all the liquid in the sample changes to vapor. In the following 3 slides, I wish to discuss with you what is the effects of different experimental conditions on the system parameters. Firstly, how the system pressure have an influence over the liquid volume fraction. Pressure plays a significant role in determining the volume fraction of the liquid in this sample because the phase change of water into water vapor occurs when the equilibrium pressure of the water in the sample crosses the chamber pressure. The rate of evaporation is also proportional to the ratio of the equilibrium pressure on chamber pressure. Also, a low chamber pressure value means that a larger portion of the sample would have an equilibrium pressure higher than the chamber pressure and can therefore change directly into vapor. And the figure shown, the 80 millibar case has the larger proportion of the liquid volume fraction in the blue region. This is because a lower chamber pressure increases the rate of evaporation, thereby therefore a larger portion of the sample changes to vapor in the given time interval. This shows the influence of pressure on the evaporation rate. As mentioned in the previous slide, a lower pressure contributes to a higher evaporation rate. In these figures, the 80 millibar case has an overall higher evaporation rate and a larger portion of the evaporation rate is in the blue region. Here, let me brief you about the influence of that the pulsing ratio has on the different operational parameters. First, let us see how this pulsing ratio affects this temperature. This slide and this next slide shows the temperature profile and isothermal contour at two different pulsing ratios. There is no significant variation in the temperature contours for the two cases. However, the temperature contours for the first case corresponding to a lower pulsing ratio of 10:5 has a slightly curved isothermal lines. This is primarily due to the fact that the sample is exposed to cool air at the atmospheric pressure more frequently when the pulsing ratio is lower. So this slide shows the effects that the pulsing ratio has on liquid volume fraction. A larger portion of the liquid volume fraction is in the blue region in the case of a higher pulsing ratio, that is the 15:5. A higher pulsing ratio means that the sample is exposed to the lower pressure for a longer duration and loses heat less frequently to cool air entering the chamber when it is open. The lower heat loss coupled with a longer duration in low pressure atmosphere together contribute to a decrease in volume fraction of the liquid when the pulsing ratio is higher. So here we can see the different effect of the pulsing ratio have on evaporation rate. The variation in the evaporation rate follows a similar trend as in the case of the liquid volume fraction shown before. With a higher pulsing ratio, a larger proportion of the sample will be devoid of water and have an evaporation rate close to zero, which is represented by the larger blue region in the 15:5 case. Evaporation rate mainly depends on the ratio of equilibrium vapor pressure of the water to that of the chamber pressure. This ratio decreases when the chamber is open and the pressure reaches 1 bar or the atmospheric pressure, which decreases the evaporation rate. When the pulsing ratio is higher than the system and system will have a higher pressure ratio for a longer duration, thereby contributing to a larger evaporation rate for a longer duration. Therefore, at a given time, the system with higher pulsing ratio will have lesser water content compared to the system with a lower pulsing ratio. So this slide shows how a change in temperature affects the different system parameters. Initially, the liquid volume fraction. A larger portion of the liquid volume fraction is in the blue region in the case when the temperature is set to 70 degrees Celsius. As this temperature increases, the amount of heat transferred from the heating plate to the sample increases. This raises the overall temperature of water in the sample. This increase in temperature leads to a higher rate of evaporation. Therefore, the higher temperature test case will have lower moisture content at any given time. Here you can see the effects of two different temperatures on the evaporation rate of the liquid. At a higher temperature, that is 70 degrees Celsius, a larger proportion of the liquid vaporizes, which is represented by the larger size of the blue region. As the temperature, equilibrium vapor pressure also increases. Therefore, a larger portion of this sample will have equilibrium vapor pressure higher than the chamber pressure, causing the phase change of the water in these regions. Hence, at a higher temperature, the higher evaporation rate leads to faster vaporization of water for the same time interval. So these are the conclusions that we have drawn from this research. In all the cases, a distinct evaporation zone was present where the liquid evaporation shifts. In case of variation of pressure, the 80 millibar case had the largest proportion of the liquid volume fraction in the zero liquid volume fraction region and the overall higher evaporation rate at any given point of time. In the case of pulsing ratio influence, a lower pulsing ratio had curved isothermal lines in comparison to a higher pulsing ratio. This may be due to the fact that more frequent heat loss to air throughout the top and side boundaries of the sample. So these are some of the references that I have used for this research. And that is the end of my presentation. And I'm thankful to the conference organizers for this opportunity. Thank you.
Thank you for your presentation.